We all know what a computer program is. It's that lifeless executable icon sitting quietly on your hard drive, waiting for you to double-click it. The program itself is a lifeless thing. It just sits there on the disk, a bunch of instructions, and maybe some static data, waiting to spring into action. But what happens the exact millisecond you open it? In the world of operating systems, a magical transformation takes place. It is the operating system that takes these bytes and gets them running, transforming the program into something useful. That lifeless file springs into action and transforms into a completely dynamic entity, the process. Informally, a process is defined simply as a running program. But behind that simple definition lies a massive engineering challenge: how to provide the illusion of many central processing units when there are only a few physical cores available, seemingly running tens or hundreds of processes at the same time. The operating system creates this illusion by virtualizing the central processing unit through time sharing, running one process for a little while, then stopping it and running another. To implement this virtualization well, the operating system strictly separates low-level machinery, called mechanisms, from high-level intelligence, called policies. Mechanisms are low-level protocols that answer the how question, like performing a context switch to stop one program and start another. Policies are algorithms that reside on top to answer the which question, such as a scheduling policy deciding which program the operating system should run right now based on historical tracking performance metrics. Separating the two allows developers easily to change scheduling algorithms without having to rethink the physical mechanism, achieving clean modular software design. To understand a running process, we can freeze time and inventory its machine state. This includes its address space memory, where instructions and static data sit, hardware registers like the program counter pointing to the next instruction, the stack pointer managing local variables, and input-output files currently open. To instantiate this state, the operating system loads bytes from disk into memory either eagerly all at once, or lazily as needed via paging and swapping, allocates a runtime stack, initializes a heap for dynamic memory allocation and free requests, sets up standard input-output, and jumps straight to the main routine. From there, the process shifts between states tracked inside a kernel structure called the process control block, moving from running instructions to ready to run, to blocked waiting on an input-output event, or even sitting as an undead zombie until its parent reads its final exit code.